All igneous rock is derived from a molten mix of minerals called magma that form a thick mantle above the iron core of the Earth. As this sketch shows, the mantle extends downward some 1,800 miles, 2,900 kilometers. It is a hot, viscous, slowly convecting semi-liquid under great pressure. Its major constituent, the mineral peridotite. The outer layer of the mantle, the lithosphere, is about 125 miles, 200 kilometers, of more or less solid but unstable rock. The outer shell of the lithosphere is some 15 relatively rigid but fractured and locally folded mobile plates of solid rock called the crust. Under the continents, the crust's average thickness is on the order of 20 miles, 32 kilometers. But under the oceans, it is less than 6 miles, 10 kilometers. These two diagrams depict the subroots taken by intrusions of magma into the continental crust and name the bodies of igneous rock thus formed. But they do not address the question, why the great difference in the thickness of the continental and oceanic crust? The answer, as shown on this chart, the lower melting points, 600 to 750 degrees Celsius, of felsic, light-colored acidic minerals with abundant silica, mainly in the form of quartz, causes them to be segregated from mafic, dark-colored basic minerals, rich in iron and magnesium, with melting points in the 1,000 to 1,200 Celsius range. And as this diagram shows, the lower specific gravity of the felsic group strongly influences their location. Consequently, felsic minerals, known collectively as Cl, tend to form the plates that are the continents, while the heavier and more refractory mafic minerals, Cma, underlie the ocean basin. The time required to cool any one of these viscous liquids to solid rock depends mainly on whether it is deposited below, upon, or above the surface of the Earth. At depth, the rate of solidification is, of course, influenced by the geothermal gradient, and to a considerable degree is governed by the size of the accumulation and its content of gases and water. But under any circumstances, intrusives solidify more slowly than extrusives because they are injected into warm strata, country rock. There, the mineral crystals that comprise the solid rock have time to grow larger than those of the same melt when it is extruded. As the chart shows, texture, the expression of crystal size, is one of the bases of igneous rock nomenclature. All coarse-textured igneous rocks, colored violet on the chart, are intrusive. All fine-textured rocks, blue, yellow, and green, are extrusive. As indicated on the bottom row of the chart, the other fundamental criterion for naming an igneous rock is the relative quantities of the felsic and mafic minerals in it. These next charts show graphically the relative proportions of these minerals in the 4 categories: felsic, intermediate, mafic, and ultramafic. As mentioned, quartz and the feldspars occur more abundantly in felsic rocks, of which the main representative is granite. Pyroxene and olivine
predominate in mafic rocks, of which the intrusive gabbro and extrusive basalt are the more common representatives. In their chemistry, felsic rocks include more sodium and potassium, while in mafic rocks, iron, magnesium, and calcium are the principal constituents. Here are snaps of the 4 main types of intrusives and their extrusive equivalents. Both have the same mineralogic composition, but the crystals of the extrusives are much smaller, generally not distinguishable to the naked eye. When this is so, the rock is said to be aphanitic. The rapidly cooled form of peridotite, komatiite, has been found but rarely. Fragmented lavas propelled violently into the air by volcanic explosions are called pyroclasts. When a lava containing much gas is ejected, it forms small bubbles enclosing glass that, when cooled, create a light-colored rock with a sponge-like texture called pumice. All lavas can form pumice. That same lava without gas and cooled very rapidly produces a glass called obsidian, most of which is black. Scorias, too, are formed by the expansion of the gas in lavas, but the vesicles have thicker walls and are larger, so the color is generally darker than that of pumice, and also differs in that its specific gravity is greater than 1. When discrete small particles of material are ejected in quantity during a volcanic eruption, they are called volcanic ash. Beds of ash consolidate into a rock called tuff. Extensive, more welded deposits of ash, pumice, and bombs formed by a nuée ardente are called ignimbrites. A nuée ardente is a huge eruption of gases in a viscous lava, controlled by gravity. The hot gas and its content of lapilli flow very rapidly, a glowing avalanche, at a speed of up to 60 miles an hour. The composition of the lava that flows from volcanoes during an eruption is the same as that of the magma that feeds it. So there are felsic, intermediate, basic, and ultrabasic lavas, but the latter are very rare. As depicted on this slide, the types of extrusives found are associated with particular environments. In Hawaii, a hotspot environment, the basalts, the surface crystallizations of gabbro, solidify in 2 types of surfaces: pahoehoe, very fluid because of its high content of gas, has a smooth or ropey surface. Aha, slightly cooler, is rough-surfaced and clinkery, but both types occur elsewhere. Here is Aha in Iceland. As mentioned, extrusive equivalents of ultramafic rocks are rare, and exposures of the ultramafics themselves, peridotite and dunite, are few, for they crop out only in the mountains formed when an oceanic plate has ridden up over a continental one, and in very old and eroded Archean terrains. Under the continents, the range of melts is mainly felsic, although thick flood basalt from fissures occupy large areas. Relatively small variations in quartz content, the relative proportions of sodium and calcium-rich plagioclase feldspar, and the percentage of amphibole all enter into naming a rock. A granite with little quartz and much orthoclase is a syenite, and a granite with more or less equal quantities of orthoclase and plagioclase and little quartz is a monzonite, and there are hundreds more. Next, metamorphic rocks
even more complex than volcanics.